Hello, everyone. Thank you for joining GeoScience and GeoEnergy webinar of 25th of June 2020 today. These webinars are hosted by my colleague and friend Sebastian Geiger from Heriot-Watt University and myself from TU Delft in the Netherlands. We are especially grateful to our keynote speakers who have supported this initiative and to you all for joining us and combat work from home isolation. Please subscribe to our YouTube channel and help us spread the words. All previous lectures are available on our YouTube channel. Also, we are delighted to announce the establishment of Poros Media Tea Time Talks series, which will start soon next week by a group of young researchers from different universities focusing on short presentations by PhD and postdoc researchers. Their announcements are available in social media, and you will find their YouTube channel if you simply search for it, Poros Media Tea Time Talks. Okay, now to the lecture of this week of GeoScience and GeoEnergy webinar series. We are pleased and honored to announce our keynote speaker of this week is Professor Anne Muggeridge from Imperial College. Anne is Total Professor of Reservoir Physics and EOR at Imperial College London. Professor Muggeridge has obtained her BSc, Bachelor's in Science in Physics from Imperial College, the same university she works today, and her PhD in Atmospheric Physics from Oxford University. After her PhD, Anne joined BP, British Petroleum Research Centre in UK for about 5 years or so, and then followed by a couple of years working in companies as software consultant with SSI Company UK, and then she joins Imperial College London in '95 and stays there until now. And was elected chair of EAGE, European Association for Geoscientists and Engineers, IOR Symposium in 2015, and local advisory committee member for EAGE annual meeting in 2013. She has been keynote speaker of many scientific events. It's no room here to bring them all here, including EAGE IOR Symposium. She has also served as ambassador for women at Imperial College, a Faculty of Engineering. That's quite a very important role to have. Her research interests include development of novel recovery processes for subsurface fluids, investigation of the geological heterogeneity and uncertainty, and numerical modeling and simulation of those processes. Her research and fundamental research, and very impactful, you all know about it, I don't need to say that, combines experiments, mathematics, and numerical analysis to answer these sort of challenging problems. She co-authors many papers in prestigious journals, which are mostly listed in her Google Scholar page. Please do pay it a visit, especially our graduate student attendees of this week. It's our pleasure and honor to host her in GeoScience and GeoEnergy webinar of this week. Please note her lecture will last for about 30 minutes, followed by questions and discussions. And like before, please type in your questions in the chat room. And you don't really need to wait until she is finished with her lecture. You can post your questions during her talk as well. And Sebastian will chair the discussion session at the end. Please also note that Sebastian is going to share his screen and show Anne's presentation slides, and Anne would kindly also notify Sebastian to flip through the slide pages. And thanks once more. The stage, or maybe better to say, the screen is yours.
Great. Thank you very much, Hadi, and thank you to you and Sebastian for organising this seminar series. It's a wonderful initiative, so we can learn about the diverse research going on in geoscience and engineering. I'm very honoured to be invited to talk to you all today. I'm going to talk to you about viscous fingering. I think most of us think we know what viscous fingering is, but hopefully I'm going to clarify what I think it is, and also outline when it matters and when it might not matter. I should point out that although I'm doing the presentation, the results I'm showing were generated by many colleagues working with me, some graduate students, Anwar, Bilal, a postdoc Andreas, and a couple of master's students, Daniel and Damien. If we could go to the next slide, please. Right, so this is a rough outline of my talk. What is viscous fingering? So we know what, or you know what I'm talking about and what I mean by viscous fingering. Remind you all of what controls viscous fingering. Why I think it can be important, not always, but sometimes, and then share with you some recent results that we have from investigating miscible viscous fingering using numerical simulation. And I'll finish off with a summary and conclusions, and a slide after that will tantalize you with some new results describing where we are going next with our research. So next slide, please. Right, so what is viscous fingering? When I'm talking about viscous fingering after this, what I'm going to talk about basically is the Saffman-Taylor instability. So we're looking at an instability that occurs when a less viscous fluid is driven through a more viscous fluid in a porous medium by an imposed pressure drop. And it was first described by Saffman and Taylor in 1958. And what you see there on the left is a numerical simulation of viscous fingering in a miscible displacement, and on the right, a bead pack experiment. And they were both meant to be performed using the same fluid and rock properties, and you can see there's quite a pleasing correspondence between the two. So we can simulate viscous fingering with numerical models. So next slide. So some other processes which people sometimes refer to as viscous fingering, but which I'm not going to cover today. So there's the Rayleigh-Taylor instability, which is fingering that looks visually, as you can see on the left, much like the viscous fingering on the previous slide, and not just because I've used the same color scheme. But in fact, it's caused by a different physical process. In this case, the red fluid is heavier than the blue fluid on the left. And therefore, there's an instability that arises because of the density difference and not because of the mobility difference between the two fluids. It can be made worse if there's a mobility difference as well. And just as an aside, if you want to try and make some Rayleigh-Taylor instability at home, a little exercise for this evening before you start possibly on your wine. If you half fill a wine glass with water, warm water, and then you very carefully inject cold dyed water on the top of the warm water, which is clear, you should see those little fingers which I've shown to you there. It's a little bit tricky, but it's quite good fun. You can then, of course, replace the water with something perhaps more palatable. Next slide, please. Okay, so other things that sometimes people refer to as viscous fingering, and again, I'm not really going to discuss. When you have flow from left to right in the top left image, and you're injecting a less viscous but also less dense fluid into a denser fluid, then of course the less dense fluid will tend to rise up over the top of the denser fluid if you inject slowly enough. And that's a gravity override or a tongue, and it's not really viscous fingering. It's too controlled by gravity. And then in the bottom left, there's a picture of what happens when you inject the same miscible fluid into a heterogeneous rock. In this case, it's a channelized rock from one layer of the SP10 Model 2 comparative study. And you can see that then the less viscous fluid channels along the high permeability channels, bypassing the more viscous fluid. Visually, it looks a bit like viscous fingering, but here the dominant property controlling the fingering is actually the permeability contrast and the correlation length there. So it's not true viscous fingering. So those on the two pictures on the left are miscible. Then we have some pictures on the right from Yu et al, which show micromodel experiments of an immiscible fluid being injected into a more viscous fluid. And that you can see is much more dendritic in the top images. And that's caused by capillary pressure within the pores, as well as a small amount of viscous effects. And as you increase the injection rate, the flow gradually becomes more compact. But that's not what I'm going to call viscous fingering here. It's what I will call capillary fingering. So if we move on to the next slide, it's a phase diagram. If you're a chemical engineer, you love dimensionless numbers and phase diagrams. And if you're not, well, hopefully you'll understand this. What I'm showing on the graph along the x-axis is a ratio of gravity to viscous number. So on the right-hand x-axis, you've got gravity-dominated flow. And on the left-hand x-axis, you've got viscous-dominated flow. And then on the y-axis, H is a measure of heterogeneity, so that the closer H is to 1, the more homogeneous a reservoir is. And the smaller H is, then the more heterogeneous it is. And what do the colours mean? Well, they're the results from a bunch of numerical simulations through a number of 2D realizations of both homogeneous and heterogeneous permeability distributions conducted at a series of rates, and then we've plotted here the breakthrough time. So if you look in the top left-hand corner where we have homogeneous viscous dominated flow, we have a breakthrough time of about 0.4, 0.35. On the top right, we've got homogeneous flow and gravity dominated displacement, where we have a gravity tongue and we have an early breakthrough time. And then as you move down in that graph, you see the increasing influence of heterogeneity. But interestingly, if you have a high enough gravity to viscous ratio, gravity will eventually conquer heterogeneity, as you'll see on the right-hand side. So what we're talking about today is the regime that's circled or squared or rectangled, whatever you like, in that green rectangle in the top left. So next slide, please. Right. So immiscible viscous fingering. So far, I've talked on the previous slide about miscible viscous fingering. Immiscible is when you have something like water being injected into oil. And as I mentioned before, you've got different kinds of behaviors ranging from capillary fingering in the bottom left of this phase diagram, compact displacements, which are like the Buckley-Leverett displacement on a continuum scale on the top left, and then viscous fingering, which is on the top right. And you can characterize which of those regimes you're in based on a capillary number, which is a pore scale capillary number, and a viscosity ratio, which is the M there. So again, when we're thinking of viscous fingering, we're in that top right regime. The other two regimes need different approaches to capture them. So next slide. Right, so what controls viscous fingering? I think we all know that, don't we? We think it must be because of the viscosity ratio. Strictly, it isn't quite the viscosity ratio, it's the mobility ratio. Obviously, that is the viscosity ratio when you have a miscible displacement, but if you have an immiscible displacement, less viscous water displacing viscous oil. On the continuum scale, you'll only see viscous fingering if the shock front mobility ratio is greater than 1. And immiscible continuum fingering tends to be much less exciting than miscible fingering, and it's also much harder to model. So we're going to focus very much on miscible displacements later on in the talk. So first control is mobility ratio. Next slide. Thank you. Second control on viscous fingering, and this applies to both miscible and immiscible, is the amount of something like diffusion in the system, and particularly the transverse diffusion. So you have flow in a particular direction and then a tendency for spreading due to molecular diffusion, dispersion, or capillary pressure. And what the diffusion does to you is it controls the number of fingers you have and their growth rate. And what you have here is a plot of growth rate on the y-axis, omega, versus wave number, which is approximately the number of fingers, on the x-axis. And these graphs are obtained by perturbation analysis, so mathematical analysis. And what you can see is that the growth rate of the fingers depends on the wave number, and that there's a sort of inverse parabola shape. And the height of that parabola is greater when there's lower diffusion, and it is lower when there's greater diffusion. And the maximum is also occurs at a higher wave number when there's lower diffusion. So what that means is basically if you have less diffusion in a system, you have more fingers. And essentially, and one definition, hopefully you'll remember for later, is that we call the peak, the wave number at which that peak occurs, the most dangerous wave number. And obviously there's a cutoff for the number of fingers, but we're focusing later on the most dangerous number, which corresponds to the maximum of that peak. So next slide, please. So then the final control on fingering, and this applies specifically to immiscible displacements, is wettability. You can see on the left, you've got more compact kind of fingering, which is on a continuum scale. Whereas on the right, it's much more on the pore scale. You can see a kind of dendritic fingers passing through this bead pack. They're both physical experiments. And the difference between the bead pack on the left is that it's water wet, initially filled with oil, and you're injecting water into that oil. On the right, it's oil wet, and you're trying to inject water into that oil wet bead pack. And that's why you get that sort of dendritic pattern there, which is much more difficult to describe, of course, with the continuum reservoir simulators that we tend to use for large scale performance prediction. So next slide. Right, so why is viscous fingering important, apart from it generates really cool pictures? It occurs, we think, in a lot of enhanced oil recovery processes, and also in carbon dioxide sequestration. Because, of course, in EOR processes, we're often injecting a miscible or immiscible gas into oil, and the gas is much less viscous than the oil. Similarly, alkali surfactant floods, there is a mobility ratio, or if you're water flooding viscous oil reservoirs. The other process that is becoming increasingly important, of course, is carbon dioxide sequestration, which is an immiscible process, but we're trying to inject less viscous carbon dioxide into more viscous water. In all these cases, what we want to do is to be able to understand where the injected fluid goes. In carbon dioxide storage, of course, we want to make sure that the carbon dioxide isn't going to find its way to somewhere we don't want it and potentially arrive at the surface. We want to keep the carbon dioxide safely underground. And it's similar in EOR processes, of course. We want to maximize oil recovery, keep the expensive injected fluid underground and just be producing oil. So those are the sort of the practical applications for engineers. But if you're a numerical modeler, you're probably quite keen on viscous fingering too, because it's modeling viscous fingering is a really good test of your simulator. It helps you understand how well it's or how big numerical diffusion effects are, and the impact of something called grid orientation error, which I'll come back to right at the end of this talk. Yes, so next slide, please. So we know viscous fingering can be important, particularly in less heterogeneous reservoirs where the fingering dominates over the heterogeneity. But you've seen in the previous slides, the fingers are very fine. We can't possibly capture that detail at the field scale because we need to have a sufficiently fine grid that the numerical diffusion in the simulator is dominating over the physical diffusion. Sorry, the physical diffusion in the simulator is dominating over the numerical diffusion. You want to make sure the fingering that you're seeing in your simulator is real fingering and not controlled by numerical error. We can't get analytical solutions, of course. Late time fingering is very non-linear, as we shall see. So instead, what most people tend to do in their modeling is replace the detailed fingering with an empirical fingering model where you average the effects of the fingering. So if you look at the right-hand diagram, what you have there is on the top a grid block, and on the bottom what might be happening in the real reservoir. And then in the real reservoir you've got in that volume, and you can see there's solvent fingering through oil, and it's distributed in a complicated way through that grid block. And we capture that in the simulator by basically saying that there's solvent and oil and something in between, which is a mixture of the two. And there are different models in the literature for capturing the mixing, which is representing the fingering. It's important to remember it's not physical mixing usually, it's apparent mixing. The most common models used are Koval, which dates back to 1963, and the Todd and Longstaff, which is again fairly long in the tooth, 1972. Todd and Longstaff model is given there below. You don't have to memorize those equations. I won't be testing you. But you can see there's a magic parameter omega in the two expressions which give you the viscosity of the oil mixture and of the solvent mixture. And that omega is basically an exponent to the two viscosities there, and the value of that exponent will essentially describe the average behavior of your fingering. Many engineers will just think no further than that. They'll invoke Todd and Longstaff and they'll put in a generic value for that mixing parameter of 2/3 or 0.67. If we could go to the next slide, please. So what are we trying to do when we're doing this modeling? If we're trying to understand how viscous fingering might affect our oil recovery or our carbon dioxide storage efficiency. So we want to do things like predict the pressure drop, water breakthrough time if it's water displacement, the development of water cut or injected fluid cut, and of course sweep efficiency at the end of our injection time. So as I said before, you can take the easy way out and use a mixing parameter for the Todd and Longstaff model of 2/3. But that mixing parameter can change depending on the physics of the fingering that's going on in the reservoir. That can affect your predictions. So the recommended approach is to use some sort of detailed simulation to calibrate your empirical fingering model for field scale simulation. But then, of course, your simulations and your choice of omega are predicated on the thought that, well, your detailed simulation must be right. So you need to do some sort of validation of your detailed fingering versus the something real, maybe some experiments, or against an analytical solution. We have done some validation of our simulator against experiments, but I'm not going to share those pictures with you here. Instead, I'm going to look at some calibration against an analytical solution, and then also some insights you get from the detailed simulation about fingering behavior. So next, there we go. Yes, so if we want to check our simulation, we want perhaps to check whether we've got the right number of initial fingers versus analysis, which is usually perturbation theory. What's the growth rate of those fingers? We need to make sure it's predicting the right sort of nonlinear interaction between your viscous fingers. And perhaps you want to know the trailing edge behavior of the fingers so that you know what the ultimate sweep of your displacement will be. So that's what you want to achieve. And in order to achieve that, it's not necessarily straightforward to model detailed fingering. You need to be able to trigger the fingers. Most simulators won't automatically produce viscous fingers. You need to impose a random permeability distribution at low level, or a random concentration distribution close to the well, just so you have some sort of variability in the system to trigger the growth rate. I've said before, we need to make sure that your physical diffusion is much bigger than your numerical dispersion. So grid refinement exercises are absolutely essential before you do any of these studies to ensure you have a converged solution. And of course, you want to minimize grid orientation errors, which are associated with the fact that fingers may tend to flow parallel to the grid when you use a regular Cartesian mesh, and therefore prevent fingering in the diagonal direction, which can give you some unrealistic fingering patterns. So next slide. Okay, so just a few little results from a recent paper. There are 4 fingering regimes when you have viscous fingering, and we've tried to capture that in the top right-hand corner, where we've got some images of the 4 regimes. And also the plot on the bottom right, it's number of fingers versus pore volumes injected. And so you've got these 4 regimes, and in the very early time of a displacement, you actually won't get viscous fingers. That occurs because you've got longitudinal diffusion, which means that when you have a step front between your injected fluid and your displaced fluid, diffusion spreads that interface much more quickly than the fingers can grow. But after a little bit of time, diffusion slows down and you get into your early time regime, which is the regime where you see the fingers begin to grow, and people would normally apply perturbation analysis. So that's where, in the bottom graph, you suddenly see a sudden increase in the number of fingers to about 8. And then after that, you enter some sort of intermediate time where you can't do mathematical analysis. The fingers grow, they interact, And on average, they decay away, as you can see in that bottom graph, until eventually, at very late time, as you can see towards the right of the graph and the bottom of the 4 fingering pictures, you end up with 1 finger. And interestingly, if you look at the sort of the middle graph, what you've got is on the y-axis, the growth of the length of the fingered zone against a logarithmic time. And you'll see that over the final 3 fingering regimes, you basically get a linear growth of the zone that's fingered, which is good news, because that means that the Todd and Longstaff model will work even when you only have that 1 finger happening in your reservoir. And of course, looking at that graph, the other takeaway message is, of course, most reservoirs have a very high aspect ratio. They're very long and very thin. So by the time your injected fluid is heading towards the production well in the subsurface, you're probably dealing with only 1 finger, which again perhaps means that Todd and Longstaff is a plausible approximation. Okay, next slide, please. So just looking at very early time to early time regime, remember that's the transition from no fingers to the maximum number of fingers, and that maximum number of fingers is actually can be calculated from perturbation analysis. I don't know if you can remember, several slides ago we had a growth rate versus wave number graph with a parabola, and I said the peak of that graph is your most dangerous wave number. Well, that corresponds to the maximum number of fingers you'll probably see in your simulation if you trigger fingering by random perturbation. And you can calculate that, ignoring longitudinal diffusion, that most dangerous number of fingers, using a very simple expression which you can see there on the left. And what that is, it's a function of R, which is the logarithm of the viscosity ratio, a transverse Peclet number, which is the PET, and then there's on the right of that expression, you can see there's an epsilon or an eta. I'm never very good with Greek letters. Apologies to those of you who are out there. You can correct me later. But that little eta or epsilon is the ratio of transverse to longitudinal dispersion. So it's the anisotropy in the dispersion. Okay, so what we found was when we first did our simulations and we plotted on the graph on the right, top right, number of fingers divided by the log of the viscosity ratio against transverse Peclet number, that we were systematically getting about half the number of fingers that were predicted by that nice little analytical formula from Tan and Homsey in 1986. And of course, at that point, the PhD student who was doing this work, Anwar, was a little bit concerned because it maybe meant that the rest of his studies so far were invalid. But we thought a bit more carefully and we read the Tan and Homsey more carefully. And we realized that, in fact, if you include longitudinal diffusion, so there's an error in that slide, it said the bottom bullet point should say including longitudinal diffusion. If you look at their results and you can plot number of fingers against time, you can see that the effect of the longitudinal diffusion is to actually reduce the number of fingers that you expect to see very quickly. So remember, in the very early time regime, you don't see those fingers because longitudinal diffusion is spreading out the front. That stabilizes it a little bit, which means that you have fewer fingers when they do eventually grow. And it turns out that that's roughly about half the number of fingers that you'd expect from that top analytical expression. So I'm throwing that out there for the rest of you who might want to check your PET numerical simulator against perturbation analysis by counting fingers. Make sure you include longitudinal diffusion. Next slide, please. Okay, so intermediate times. So what we have here, the red and the blue images are snapshots of viscous fingering at different for different viscosity ratios and transverse Peclet numbers at a particular time. So you can actually see the fingers at a particular time. But if you look at the second and the fourth column there, what you see in those sort of rainbows that look like track the trajectory of the fingers, what you're actually doing, we're tracking the trajectory of a fingertip over time so that you can actually see the interactions of the fingers. And you can see different interactions. So let's see, this is where it would be great to point with a mouse. But if you think about the second from the left, second down image, you can see there's a rectangle with SP beside it. There we're seeing that a finger is spreading over time. It's spreading transverse to the flow direction. The image below that, you can see a rectangle with CO, and you can see something called coalescence. Thank you, Sebastian, that's great. Where you can see two fingers merging together. And then on to the right, little bit to the right of that, you see TS, which is where a fingertip has split. And you can see other behaviors on the top right. Unusually, you get double coalescence, where two fingers are merging into one. You have a very complex behavior going on in the bottom right, but I should have mentioned one of the important behaviors, sorry, Sebastian, is the bottom image in the second column. You can see SH shielding, where a finger is growing and stealing material from adjacent fingers, so they stop growing. So you can see those interactions, and then I got a master's student to do a load of simulations with different perturbations, so we had good statistics. And what he's plotted in that graph on the left is the proportion of growth events in a displacement over a period of time against the log of the viscosity ratio on the x-axis and the transverse Peclet number on the y-axis going into the image. What you can see, as perhaps you might expect, the number of growth events, which include tip splitting and branching, increases as viscosity ratio increases and transverse diffusion is lower. Okay, late time, please, on the next slide. I will be done soon. It's only slightly over half an hour. I apologise. So late time behaviour, as I said earlier, I think that's possibly most relevant to most oil reservoirs. At late time, it seems all these fingering patterns tend to decay to a single finger. And it seems like that time scale is related to the most dangerous wave number you get from perturbation analysis. And that is the number that you can calculate from that analytical expression, and the growth rate of that most dangerous wave number. And what you can see on the top right graph is we've scaled the number of fingers by the most dangerous wave number against a dimensionless diffusive time multiplied by the growth rate. And you can see that we've got graphs from a number of different cases with different Peclet numbers, transverse Peclet numbers, and different ratios of transverse to longitudinal dispersion, and they all collapse very neatly onto one another. And you can see they all tend to a single finger at about the right time. And again, we've got that nice graph underneath which shows that the length of the mixing zone seems to grow linearly with pore volumes injected over all time, which again is nice because it means Todd and Longstaff will work even in this very late time fingering regime. Okay, I think this is the conclusions coming up, please. Yes. So, viscous fingering. What I've talked about is an instability caused by a less viscous finger fluid displacing a more viscous fluid, so by an imposed pressure drop. And the fingering is controlled by a balance between the viscous pressure drop, which is the mobility ratio, and diffusion. We can see it in EOR processes, which are usually miscible. We can also see it in CO2 sequestration, which is more typically immiscible when you're thinking about viscous fingering. And you can parameterize that by a Todd and Longstaff model, ideally calibrated against detailed numerical simulation. So that's a sort of summary of the first part of the talk. The second part, I showed you some pretty pictures looking at the dynamics of viscous fingering in line drives. So you've got the 4 fingering regimes, but it seems that for a variety of inputs that we tried, you always get this one finger. That's been seen by other people as well. And that fingering zone seems to grow linearly. And most interestingly, we can scale the number of fingers and the time at which you head to that single finger is directly related to the most dangerous wave number and growth rate obtained from very simple perturbation analysis, because those happen to depend, well, inevitably those depend on a transverse Peclet number, logarithm of viscosity ratio, and the ratio of transverse to longitudinal dispersion. So one final slide, where next? There's always more fun to be had with fingering. Some work that we've got in progress looking at 3D viscous fingering. To do that, you really need a dynamic adaptive mesh so that you don't use up enormous amounts of computer resources and wait a year for the results. And having a little look at immiscible fingering particularly. Preliminary results suggest they behave similarly to miscible fingers, but you can get a continuous cycle of tip splitting, merging, tip splitting and merging. So you don't necessarily always get this single finger. At least that's what we've seen in our simulations. And then the big question out there is radial fingering dynamics, which is perhaps relevant. Well, it is relevant to any displacement where you're using a vertical well in the subsurface, because of course the displaced fluid moves out radially from the well. And what I'm showing there are some experimental results from a heli-Shaw cell and our attempt to simulate those with a finite difference simulation using a Cartesian grid. And as I promised you, this is where you see some grid orientation error. The bottom pictures are simulation, and you can see that the fingers very much want to travel along the rows and columns of the grid rather than heading directly off to the production well. Interestingly, although the fingering pattern doesn't look that great, I haven't shown you there, but the average behavior in terms of recovery and breakthrough time isn't too bad for those. Right, well, thank you very much. I should also note that these were this research was sponsored by BP and Total, amongst others. So we're very grateful to their funding, and I look forward to hearing your questions.
Thank you very much, Anne, for the very interesting presentation and quite engaging. We have already received a number of questions. I leave the floor to Sebastian to chair the discussion.
Thank you very much, Anne, for the questions. Now start putting them together on the screen here and read them out, and I try to group them so thematically. So the first one is from Musa Hosseini-Mehr, who asks, given the high amount of heterogeneity and geologic uncertainty in many reservoirs, can we just assume that the fluid-fluid interfaces are primarily dominated by heterogeneity rather than fingering?
Yes, I think that's absolutely true. I think in the majority of very heterogeneous reservoirs, what you might describe as viscous fingering is in fact a channeling behavior. But you can interestingly adapt the viscous fingering models to include heterogeneity with a factor that essentially multiplies the effective viscosity ratio that represents that channeling. I haven't really discussed that here. But yes, in most cases, you probably want to just think about the long correlation length heterogeneity.
Related to that is a question by Laila Hashemi. Is there a way of quantifying how the presence of fractures impact fingering?
Okay, I suspect if you're talking about conductive fractures here, and if so, then what you're probably not going to see much in the way of the viscous fingering I've described, but much more of the channeling, because of course the injected fluid will just whistle through the fractures very, very quickly, and your recovery will be dominated by the fractures. It's a channeling effect.
Thank you. And we have a question from Servi Naderi, who was doing water flooding. Is it the Peters and flexibility criteria? Is the Peters and flexibility criteria necessary and sufficient condition for viscous fingering effects? Or could we say this criteria is only a sufficient condition?
All right, you're testing my memory there. Peters and Flock stability criterion. I can't remember exactly what that is, but I can say that the main thing is to ensure that your shock front mobility ratio is greater than 1. Just having a viscosity ratio greater than 1 doesn't necessarily mean you'll get continuum viscous fingering.
So we're going to test your knowledge a little bit further then, Anne. And follow-up question from Sally. Ask, is there any other criteria to predict the onset of stability in other flooding systems prone to fingering, such as gas floods? And thank you very much for the great talk.
Well, thank you, Survey. That's a pleasure. I'm assuming you're again talking about immiscible processes. And again, I would suggest you look at your shock front mobility ratio to see if you're going to get true viscous fingering. Yeah, obviously, if it's a miscible displacement, you want to look at the viscosity ratio. But if it's in both those cases, if it's a gas flood, you've probably got a tendency for the gas to override the oil. And in that case, you may want to look at your viscous to gravity number. You know, there are different formulae out there. I've given you my favorite one, but there are, I don't know, 10 or 20 out there in literature. So I would see whether your viscous to gravity number is very viscous dominated or very gravity dominated. Obviously, if it's viscous dominated, you'll get viscous fingering if you don't have a lot of heterogeneity. If you have a very low flow rate, which is perhaps the case, a distance from the well, you may well get gravity override.
Thank you, Anne. We have a question from Precious Baby. If the fingers do not merge into one at the late time in the late time regime, as the injected fluid migrates to the producer, is the Todd-Longstaff model still appropriate for modeling miscible viscous fingering?
Oh yes, definitely. Todd-Longstaff was originally developed for the case where you have lots of fingers. That's where most of the simulations were initially done, because we didn't have the compute power we have today. So they tended to use aspect ratios of close to 1 for the calibration of it. And it's just pleasing that it seems to work well for the fingering regime grows linearly even when you have one finger, we haven't actually checked the Todd and Longstaff model directly against that. So I'm hedging my bets there.
Thank you. We do have two related questions that are about boundary conditions. I'm going to read both of them one by one. So the first one is from Qingwang Yuan. Great presentation. Thanks a lot. Could you please explain why the fingering does not reach the right boundary even after 5 pore volumes injected?
Yeah.
Is that because of the moving reference frame?
Yeah. No, it's an Eulerian framework. The reason is how we've defined pore volumes injected. I should have said earlier, because we were initially investigating the effect of aspect ratio on the fingering. We defined a pore volume based on the width of the system rather than on the width times the length. So if you imagine one pore volume is for a square system, if you then keep the width the same and you increase the length by a factor of 5, that would be 5 pore volumes injected. I hope that makes sense.
Mm-hmm. So Bill Rossen, last week's speaker, was intensely listening to your talk. Great talk. One of your early slides is showing a decay of number of fingers. Seem to show that the fingers avoid the top and bottom edges. Is that numerical? Would results differ with the wraparound boundary conditions? It's again a question around the boundary conditions.
I suspect it is, Bill. We did some tests which I haven't shown there, and again, this is to do with the boundaries and the use of a Cartesian mesh and the no flow perpendicular to the boundary. And what that seems to do is that the fingers prefer to flow away from the edges. We have compared our results against other people's results where they've used wraparound boundary conditions, and we get very, very similar behavior. We can't see anything significantly different in terms of numbers and fingers and other behaviors.
And staying on the topic of setting up the model, Helton de Siriaco, I hope I pronounced this correctly. If not, my sincere apologies, asked, do you think mesh orientation errors can be overcome by using unstructured mesh?
We very much hope so, because that's where we're going next.
Okay. So coming back then again around gridding issues, Qingwang Yuan also asked, could you please evaluate the capability and accuracy using commercial simulators such as CMG or CLIPS to simulate fingering for lab scale simulations with inverted commas very fine grids? I think probably evaluate comment on.
Yes, so I think you're talking about the ability to model the details of the fingering rather than the average fingering. And yes, you can certainly use either of those simulators to model miscible viscous fingering. We've done that quite successfully. You need a much finer mesh than we used because our simulator is a higher order method. And the other thing you need to do is there's a paper by Lantz in the SPE, I can't remember the number, where he describes how you can construct relative permeabilities to mimic miscible displacement in an ordinary simulator like any of the CMG family or Eclipse family. So yes, you just put in those rel perms, use a fine grid, obviously do a grid refinement study to check it's fine enough, use a perturbation to kick off the fingers, and you should be happy.
Great, thank you, Anne. We do have a question from Siddhartha Shaomi. Again, thank you for the presentation. I should point out there are lots and lots of comments on Genesis and Jakuyu, Hassan Mahani, many others who thank you for your excellent talk. So Siddhartha asked, can you comment on the saturation profile injected fluid content profile along the length of the finger, both at the early time finger, for the early time fingers and the late time single finger?
Okay, that's a really good question. If I had the ability to share my screen, I would show you some pictures, and I'll try and describe it to you in words. So if you imagine an early time and you're looking at a miscible viscous finger and the profile along it, the concentration along that very early finger is, the maximum concentration is 1. And it'll decay very, very slowly, and then of course you'll have a dispersion at the fingertip due to the longitudinal dispersion. If you then look at the late time single viscous finger and you plot it versus time, and we did that, I think, in our paper, the Abdul Hamid and Muggeridge this year paper, you will see that the concentration along the finger decays and becomes much lower, so that at the tip it's maybe 0.2 or 0.3 compared with 1 to begin with. And over time it'll get lower, and that's because transverse dispersion is spreading the finger sideways. And so therefore, over time, you are seeing less and less miscible fluid within the finger.
Moving on to the field scale, Kishan Kumar asks, again, thank you for the presentation. How can we monitor fingering and value models in the fields?
That's a $60 million question, isn't it? Wouldn't we love to be able to see the viscous fingering in a real field? Unfortunately, I don't think you're going to stand much chance of seeing the detailed sort of fingers we see in our models, because the only thing you have for looking within the reservoir is seismic surveying, and it just doesn't give you sufficient resolution. You can see channeling. I mean, people have seen that. Where is it? There's a Sleipner, of course. There's what appears to be a finger, but is probably channeling, that people have seen when they inject CO2 into water. Validation against the field, I think you can verify, you can produce the same answers, but you can't be 100% sure that what you're modeling is what's really going on. Sorry.
Thank you. Jillian Pickup asks, are there any situations where viscous fingering is an advantage? I expect it's nearly always a disadvantage due to causing reduction in sweep.
Good question, Gillian. I speculate whether it might actually be a good thing in situations like CO2 sequestration, where you want to enhance dissolution, because of course you've got a larger surface area if you have fingering compared with if you have a conforming front, and therefore if you have a larger surface area, there's more opportunity for dissolution. So there's perhaps increasing the rate at which you dissolve your CO2 in the water and keep it out of harm's way.
It was actually the same question I had in mind asking you, so thank you for answering that. And Peter Mazzari, can relative permeabilities be affected by viscous fingering?
Oh, yes. Well, probably. It's because, of course, it depends how you measure your relative permeabilities. I mean, there's a whole area for discussion in how you measure relative permeability and what's most appropriate for a reservoir. But if you measure rel perms by an unsteady state method, you may inadvertently have viscous fingering in the front when you're injecting a less viscous fluid into a more viscous fluid. And of course, when you then invert the results to get your rel perms, they will capture the fingering, so they'll be kind of empirical. These days, of course, you can check whether that's happening using a CT scanner. If you don't have a CT scanner, you can try and prevent it by have a vertical core and injecting the lighter fluid above the heavier fluid. Of course, if you have two fluids that have the same density, gravity isn't going to stabilize the fingering. So yeah, so treat REL perms with great caution at all times, I think, is the bottom line.
There's one final question from Precious Baby. Thanks again for the great talk. Fingering are best captured in fine grids. Is it possible to upscale fine scale miscible fingers to a coarser scale? How realistic would the results be?
Yes, exactly. I mean, that's what we're trying to do with the Todd and Longstaff model. There's a whole zoo of different empirical viscous fingering models, which are basically upscaling the fine scale fingering out there. It just happens Todd and Longstaff is implemented in most commercial simulators. Yeah, it used to be in the 90s, I think there'd be every PhD student would be generating their own preferred viscous fingering empirical model. And yes, on average, you get very good results. There's again a literature out there which shows these fingering models average fingering models work very well. So thank you, Precious.
Thank you much. And a few more questions coming in, but we do run out of time. So as always, apologies if I have missed one of your questions and couldn't answer them. Again, just to emphasize, there are lots of thank you notes in the chat for your great talk. So thank you very much on behalf of everyone listening and for that presentation. And I hand over to Hadi for some last words.
Yes, thank you very much. And once more, and thank you all for the very engaging questions. I would like to announce that our next week speaker is Sally Benson from Stanford University, and Sally would speak about CO2 storage in heterogeneous subsurface formations. So stay happy, healthy, and tuned until next week, and have a nice week ahead.
See you all next week.
Yes, see you next week. Thank you all. Thank you. Bye-bye.
Thank you, everyone.